Greetings, Saintsmen. This is the lecture for your section on inductive reasoning within your textbook. A few things that I want to address as we're going forward. We have the notion of what are called conditional statements, which we discussed in class when we reviewed that packet. And these, again, are if-then statements. Okay, so we're going to take some if-then statements and we're going to deconstruct them, and there's going to be a few different versions that we need to consider logically. The first conditional statement is if Mr. Granados punched a student, then he was fired. We can make the hypothesis Mr. Granados punched a student, statement P, right? If then, we have the arrow showing that then he was fired, statement Q. Okay, so three various iterations that we will get of that. First of all, we have the converse of the statement. Converse means that we reverse, or as sometimes you'll hear me say, that we flip the hypothesis and conclusion, right? So in this case, it would be constructed as if Mr. Granados was fired, then he punched a student. Now, of course, the logical truth between these two things, the conditional statement and then these various iterations, they don't have to be connected, right? So in this case, we have if Q arrow P, right? If Q, then P. And that's not necessarily true. If Mr. Granados was fired, then he punched a student. It's not necessarily true, right? It could be true, but we wouldn't actually say that's true. We'd actually say that is false. Mr. Granados obviously could be fired for other reasons. Like, for example, he knows nothing about math. Or he committed arson or something else, another crime that got him fired. So it doesn't necessarily need to be revolving around punching. Related to the converse is what we call the inverse of a statement, where we're going to negate the hypothesis and conclusion of that original conditional statement. So in this case, going back to our original conditional statement, so we're going to take if Mr. Granados did not punch a student, then he was not fired. And I'm going to go ahead and emphasize not. Remember, when we negate, it means that we make something not true. So I'm going to go ahead and put that in all caps here, not. Okay? Again, the notation we use, the squiggle for not, so squiggle P, arrow, squiggle Q, right? If not P, then not Q. And again, this one doesn't necessarily need to be true. This would actually be a false statement. Again, if he did not punch a student, just restraining myself from punching students is not what keeps me from being fired. Other things could lead to my eventual dismissal. So just, again, some food for thought. The contrapositive is when we reverse and negate both the hypothesis and conclusion simultaneously. Now, I know you know the word simultaneously because you probably played too many video games, right? Press X and Y simultaneously. After all, this is being broadcast on Twitch. Gentlemen, this is the logical equivalent of the original conditional statement. In fact, some of you will become attorneys someday, and when you are taking the law school admissions test, often examining the contrapositive will help you determine the truth of the original conditional statement. For example, we're going to reverse this. If Mr. Granados was not fired, then he did not punch a student, which would be true, because obviously the student punching would lead to the firing. Notation-wise, this will be squiggle Q, arrow, squiggle P, right? So if not P, then not, if not Q, then not P. So that's what these things would look like. I want us to consider going back to our lesson regarding inductive reasoning, which of course is going to be something that's going to occur through pattern. So there's a famous mathematician named Carl Gauss, and Gauss is famous for what's referred to like his magical equation, but it's effectively just how to do a summation. According to legend, he had kind of come up with this when he was a small child, and he was given a problem as busy work to add the first 1,000 numbers. He started to do it, and then he thought about it for a moment and came up with a solution, and then just kind of walked away, and he was done. And I always remember this because I can do this with the first 10 numbers rather easily, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? You know, rather than doing an actual summation there, what people will start to do is they're going to start to pair these things, right? So like, for example, we could do 1 and 9, 2 and 8, 3 and 7, 4 and 6, right? So we have 10, 10, 10, 10, and 10, and then plus 5 more, so we're going to have a total of 55, right? Another way to consider this guy is, again, we could pair these things. Rather than just doing making groups of 10, we actually just group first and last, and then everything is going to have a pair, right? So for example, 1 and 10 right here, that's going to be 11, but how many 11s are we going to have? 1, 2, 3, right? Because 2 and 9, 3 and 8, 4 and 7, 5 and 6. We're going to have 5 of those, 5 times 11 being 55. Okay, leads moreover to this, like there's these dot patterns. These are actually called the figure-8 numbers. In fact, this last one's going to look like bowling pins, right? And we can actually add these guys. This is related to the same thing. We have 1, 3, right? 1 plus 2 plus 3 is 6. 1 plus 2 plus 3 plus 4 is 10. Okay? But what we're adding is we're adding in what that last row would be. So in other words, we're going to have n being the number that we're at, the termed number, and then we're going to take the sum at whatever that is. All right. So here, this is the first term, this is the second term, this is the third term, this is the fourth term, right? So we're going to say 1, 2, 3, and 4. And so in other words, S sub n, in other words, this guy is n, where n is equal to 1. So this is S sub 1, which is equal to 1. This guy would be S sub 2, which is equal to 3. So 1, 3. S sub 3 is equal to 6. Moreover, to S sub 10. So to do this, right, what we're doing is we're just adding that last row, right? So we can take that previous number and then notice the last row. For example, in n equals 4, that has 4 dots in it, right? So whatever number term we're in, that's how many are going to be in that last row. So all we have to do is just take whatever row we're in, right, and add the previous sum, right? So 4 plus 6 is how we get 10. Or, here we go, 3 plus 3 is how we're going to get 6. So describing that verbally, we would say that each time we add a number, it increases by the previous term. The term being how we would number the sequence, right? First term, second term, etc. So consider this. Let's say we have S sub 2, and that guy's equal to 3, and that's because n is equal to 2, right? Moreover, we're going to take S sub 3, and that is equal to, well, how do we get S sub 3? Well, it's 6, but that's because we took 3, the number we're on, and we added S sub 2. Or even S sub 4, we took 4, right, and we added S sub 3. And S sub 3, of course, right, was 6. So if I'm trying to find any number in the sequence, S sub n, well, take a look at what we did here. Pattern-wise, it's going to be n plus the previous term, which we describe as S sub n minus 1. Okay? Next lesson, we'll discuss what that is, but if we're looking for patterns on how to do things, that means that we are utilizing inductive reasoning. which is reasoning through pattern. A conjecture is going to be a guess or theory we're going to make about some piece of information. So in other words, with conjecture, it's when we see a pattern in something and we're going to try to make some sort of guess or theory about that. And then the counterexample is the unfortunate part, because all that does is it blows apart what our pattern is. It's an example that disproves the conjecture. All we need is a single counterexample to totally foil whatever guess we have about this. Pretty much the weakness to inductive reasoning. Your homework regarding patterns and the first part of inductive reasoning is published on Canvas. Good luck.